In this presentation, I'm going to summarize my critical review of a paper done on the cadmium sulfide nanowires with a lead sulfide coating used as a liquefied petroleum gas sensor. The paper was conducted by B.R. Sankapale and their colleagues. First, we will explore the purpose of the paper in terms of what they were trying to achieve, followed by an explanation of the background knowledge regarding the underlying physics principles of the paper. Next, we will describe the operating principle of the sensor, followed by the various methodologies employed by the authors in order to test the validity and usefulness of the sensor. Finally, we will end with a conclusion summarizing the findings of the paper and the extent of its potential for future use. The aim of the research paper was in creating a liquid petroleum gas sensor that was able to operate at room temperatures with a high sensitivity and ideally a low cost. A quick response time is also a positive attribute that the research authors were looking for. The important background principles for understanding how the sensor works include the creation of the cadmium sulfide nanowires along with the synthesis of the lead sulfide nanoparticles by using the Sylar method. The creation of the cadmium sulfide nanowires is done using a soft chemical route, where the cadmium hydroxide nanowire bundles are created before being converted into cadmium sulfide nanorods by utilizing an anion exchange route. The synthesis of the cadmium hydroxide is done by a chemical bath deposition where a source amount of cadmium chloride is used. Then an alkaline pH change is induced by adding drops of ammonia and stirring the aqueous solution. This is done until a pH of 12 is reached, and then the precipitate of the cadmium hydroxide nanowire bundles is extracted, filtered, dried out, and collected. The next step of the conversion to cadmium sulfide is done by mixing the precipitate with a solution of sodium sulfide for 30 minutes until a color change from white to yellow can be observed. In order to verify the integrity of the crystal structure and conversion to the cadmium sulfide powdered form, an X-ray diffractometer can be used. Next, we will describe the process by which lead sulfide nanoparticles are layered onto the cadmium sulfide nanowires. This method used is called Sylar, which is an abbreviation for successive ionic layer adsorption, followed by a reaction which completes the coating. Beginning with the Sylar cycle, it allows for the adsorption of the lead species for 20 seconds, after which distilled water will remove any excess or loosely bonded particles before the introduction of a sodium sulfide solution, which helps the reaction between the lead and the sulfate ions in order to achieve a stable form of lead sulfide. Finally, water is used once more to rinse any unreacted particles, leaving only the desired product behind, and the process is repeated for multiple Sylar cycles. Next, we will explain a bit about what a heterojunction is and how this ties into the operating principle of the sensor. A heterojunction is an interface between two different semiconducting materials, resulting in an uneven energy gap between the molecular layers, which is an energy range in a solid substance where no electronic states can exist. This is useful for sensing gases because of the high surface-to-volume ratio, high surface sensitivity, and very good semiconducting properties within a highly porous structure that allows for the movement of gas molecules to occur easily. The operating principle of the gas sensor is based on p and n type conductivities of both of the two semiconductors, where the cadmium sulfide exhibits p and the lead sulfide shows n conductivity. The difference between the two types of conductivities is that for a p-type semiconductor, the conduction occurs through the movement of positively charged holes, whilst for an n-type semiconductor, the conduction is due to the movement of excess electrons. The heterojunction between the two compounds create a band gap in the valence levels, and if overlapping to a sufficient degree, can exhibit conductive properties. Here is a diagram that shows the separation of charges that can be seen between the heterojunction. Next, we will describe the composition of the LPG sensor, which is effectively a layering of glass, FTO, and then the lead sulfate coated cadmium sulfide nanowires and can be seen on the diagram on the slide. The two other charts show the barrier height, which is simply the difference between the metal work function and a semiconductor. And we can see how this height is lowered when the surrounding gas is changed from air to LPG. Here we can see the current density voltage curves show non-ohmic behavior, which is an indication of the presence of a heterojunction. The chart shows the distribution of different current densities at different voltages for the sensor for each line, representing a different LPG concentration, where A is air and B is 300 parts per million LPG, with each subsequent line increasing by 300 more ppm. From this diagram, it is clear that around 1 volt range, we get the best distribution for the current density and therefore a very good reading from the sensor. The authors also calculated the gas response using this formula and tabulated the results in a chart. We can see from the chart that the gas response ranges from 30 to about 60%, and the reasons for this 30% change in responsiveness can be due to the unimolecular layer of gas molecules forming on the surface of the interface that would increase the interaction, resulting in a higher response. After the concentration passes 1200 ppm, then the gas response decreases, and this could be explained thanks to the formation of multiple gas molecular layers at the junction's interface, which give a worse reading. The quality of the sensing mechanism can be affected by a number of characteristics of the device, which include the nanowire's diameter, the aspect ratio of each of the individual nanowires, the physical changes at the interface due to the presence of gas, the absorption, desorption enthalpies, along with the ambient relative humidity around the sensor. These parameters were reported in a different paper by Lupin and his colleagues in a zinc oxide nanowire study. The authors of the paper also investigated a response transient curve for the first two LPG concentration interactions done at a fixed voltage of 1 volt, which had a gas response of about 60%. The symmetry of this response transient curve shows the stability and repeatability of the result, and when being compared to different results of heterojunction sensors, then the paper reported that the lead sulfide and cadmium sulfide heterojunction gives a very fast response time with better gas responses than most of the other heterojunctions. In summary, the paper clearly explains the science of developing the LPG sensor and the procedure by which it's done. A clear description of the physics behind the operating principle would give the readers a clearer understanding of how the sensor works, but the paper assumes that the reader has a good understanding of the physics behind the working principles of semiconductors and heterojunctions. The authors reported that this type of sensor has a low cost in terms of production and taking into account the high gas response sensitivity. The design shows much promise in terms of providing a better alternative than other sensors available today. Due to this paper definitely has grounds for being written in terms of uniqueness and potential for new applications. To summarize the operating principle, the lead sulfide and cadmium sulfide LPG sensor is based upon the creation of a heterojunction between the two semiconductors, which then creates a barrier height and depletion region capable of altering the current density when subject to a voltage change with the presence of LPG between the heterojunction. The main advantages of this design are the low cost and easy production of the system through the chemical process, along with very fast response times and the higher gas response sensitivity when compared to its counterparts. The stability of the sensor was also proven in the report by verifying the repeatability of the result, which is an important aspect in making a good sensor. In conclusion, the development of this type of sensor is very useful and can be used in applications for sensing LPG leaks at a low cost to a high degree of accuracy. Thank you for your time, and I hope you found this presentation. Thank you for your time, and I hope this presentation was educational on this type of LPG sensor and the work done by the research team that wrote this paper.